Well, some of you might have noticed that when you're doing this simulator, that when you change the mass of the sun, crazy things happen. But when you change the mass of the planet, it doesn't seem to change very much. So we've got the sun and the earth here going just normal. And we're going to make one full year. Slow it down here so we can get right on the line. Oh, so pretty much 1 year out. But if I change the mass of the Earth, let's say I double it, you'd think you'd see a pretty big change, right? But when we play it, let's fast forward through there. As we come around again, got a slow motion. So we should end up right around 732, 33 days. Boom. So it didn't seem to make a difference. Changing the planet mass didn't seem to change the amount of time it took to go around. But isn't that what we said? That, if it weighs more, that you would have to go faster to keep it in gravity and without being pulled in, but yet it doesn't seem to have made a difference. It's still exactly 365, 366 days around. Well, we're going to look at that and try and look at it with a little bit more detail, because this doesn't give us a lot of details. It gives us days, but it doesn't really give us speed or some of the other details. So we're going to look at a different simulator and see what that can show us. So here we are with the Universe Sandbox simulator, the one that we showed in that one video, and you can see it's got the solar system here with the planet spinning around, and it's all happening fairly quickly with 14.5 days per second, so everything's spinning fairly quickly. I want to pause for a second. We're going to select Earth. I want to look at its information. We can see here it gives a lot of information, like it'll give us the mass here that the Earth weighs, well, the equivalent of one Earth, because it is the Earth. We can come down here and it'll give us the speed, about how quickly it's traveling. We've got the orbital period, how many days it takes to orbit the sun. So if we just, right now the standard, one Earth is about 30.3 kilometers per second. It takes 365 days. So let's just play it a little bit and see what happens. Now you can see the speed changes a little bit, like it's going to drop down to below 30. And it keeps going down, so it's down to 29.3. And that's the lowest it goes. But then it starts to speed up again. And it's going to work its way back up to 30.2, 30.3. And that's the highest. So we got a 29.3 to 30.3 sort of range. Okay, so let's see what happens if I change the mass. Let's say just for the heck of it, let's just double it. Oops, not 20, double it, just like we did in the other simulator. And let's see what happens to that. So everything gets adjusted. It's still saying 365 days, so let's see what happens. Does our speed change at all? So we're still running 29.5, 6, 9, 30, 1, 2, 30.3, and it's going to work its way back down again, and it comes down again to 29.3 is the lowest. So same range as before, as if we had just one Earth mass. Okay, so that didn't make a difference. So let's do some other stuff. Let's try 5 times as big. Let's see if that makes a difference. Well, we're still sitting at 365 days. Let's see what happens to our speed. Does that change at all? Well, we're still sitting at 30.3 as the highest. And as we come down the other side, 29.3 is the lowest. Huh. It looks almost as if changing the mass doesn't change the speed and doesn't change the orbital period. Well, let's go a little bit crazier. Let's make it 20 times bigger. 20 times bigger. Let's see what happens there. So at 20 times bigger, 20 times heavier, what's our velocity going to do? It's still down to 29.4, 29.3. Orbital period is still 365. And then speed's coming back up, 30.1, 30.2, 30.3, and then it stops. We still get, even at 20 times the mass of the Earth, we're still looking at the same speed and same orbital period. Alright, let's change this a little. Let's say we do 100 times. See if that changes anything. And just for the heck of it, I'm going to change, well, let's see, 30.3, still sitting at 30.3. I'm going to compare this to, say, Jupiter. So 100 times the Earth is still less than a third of Jupiter. So, okay. But we're still looking at the same orbital periods, same velocities. Well, let's make the Earth equal to 1 Jupiter. Oh, look at that. We lost a day. We're now down to 364. What happens to our speeds? We're at 30.1. Remember, the highest we got was 30.3, and we're still sitting at 30.3. The lowest we had was 29.3, and we're still looking at that. So, wonder what's going on here. Let's change this. And you know what? I'm going to change it to the sun. I'm going to compare it to the sun because 1 Jupiter is, like nothing compared to the sun. As big as Jupiter is, its mass is nothing compared to how big and heavy and massive the sun is. So let's say we take the Earth and we make it equal to 1/10 the sun. At 1/10 the sun's mass. Now notice the orbital period has gone down to 306. We've lost like 60 days on our orbital period. Let's check out the speed, see what happens there. Oh, look, we're going up to 32, 33, 34, 35, 36. 36 is, oh my gosh, look what's happened over here. The Earth has gotten so much gravity it's actually pulling the sun around. Mercury's being all screwy. What happened to Venus? Venus is way out of line. But look at how much we had to increase the mass of the Earth in order to change the orbital period and to change our speeds. Let's say, what if we made the Earth a quarter of the sun's mass? What would that do? Well, now we're down to 249 days to orbit the sun. Well, let's see what kind of craziness. Oh my goodness, look at this. Now the Earth and the sun are like pulling on each other. Venus is just going off into nowhere. Mars is going off who knows where. And our speeds, look at how fast it's up to now. Almost 45 kilometers a second, and then down to 30, almost 30 kilometers a second. But look at how much of a change we had to make, though. And a lot of it has to do with, if we take, here's a quarter of the sun. How much is a quarter of the sun compared to the Earth? A quarter of the sun is 83,000 Earths. So we're talking about so much mass in this sun that even changing the mass of the Earth, like doubling it or multiplying it times 10, is so insignificant compared to the sun and the amount of gravity the sun is putting out, that changing the Earth is not really going to do a whole lot for its speed or orbital period. But if we, let's reset everything here, reload. But if I were to change the sun just the tiniest little bit, let's say if I was to make this, oh, I don't know, let's make it a little bit lighter. Let's say 3/4, 0.75, which is 786 Jupiters, or almost 250,000 Earths. That's a lot. So let's look at Earth. What does that do to Earth? So the orbital period for Earth, by bringing the sun down 1/4 of its mass, the Earth's orbital period is now over 2 years. It takes 2 years for the Earth to go around the sun because the gravity has got that much less, then the Earth has gotten that much slower to take that time. So what we're really seeing here is the gravity of the sun, because it's so massive, so overpowers any gravity of the Earth that anything we change on the Earth is going to be insignificant compared to this. So that's why when you're doing that simulator and you're doubling the Earth or making it half size, it doesn't really change anything, because compared to the sun, it's really nothing. The difference between these two and their mass and their gravity is so hugely different that any change to the Earth, unless we make the Earth like the sun, changing the Earth is going to make no difference really in how fast it travels or how long it takes to go around, because the gravity of the sun is really what the main power is in this equation. That's so much stronger, it has so much more effect that it overwhelms any other changes we make, unless we make, like massive changes. Let's make this, just for funsies, let's make this equal to 1 sun. Let's have 2 suns, see what happens here. So here we got our real sun. Now we got Earth as a sun. Look at pulling our sun out. And they're going to whip around each other. There goes our sun. Here's the Earth as its own sun. Now it pulls the sun back again. And then that pulls the Earth back. And they just start whipping around each other. Venus is flying out. Jupiter's being pulled in. Yeah. That's some crazy, crazy stuff. Anyway, so that's what's going on. That's why when you're doing that simulator on the PhET system, that when you doubled the Earth, it didn't make a difference, just because the Earth is so light. Even if you double it, it's compared to the gravity of the sun, the Earth is so light that it really makes absolutely no difference. So there you go. Mystery explained.